Welcome to New Dynasty Academy. Today you will learn the formal proofs for Euclidean geometry theorems. These proofs contribute to approximately 12 to 15 marks of your final paper 2 examination. You must memorize or be able to memorize the specific steps that we'll be using in proving these theorems so that you secure these marks that are given in your paper 2. We will focus on the circle geometry theorems only for today. That is what is required for your grade 11 and grade 12 syllabus. So let us begin with the first theorem. The first theorem says the line drawn from the center of a circle perpendicular to the chord bisects the chord. So what is given in this circle? We are given that OJ is perpendicular to AC and OJ is drawn from the center and it is perpendicular to the chord AC. So we are required to prove that AJ is equals to AC. So in our proof, the first thing that you need to do when you're proving this type of theorems, it is for you to do the construction. So let's go on and say construction. What did we do? We've already constructed here in this figure, but what did we do? We have joined OA and OC. So you say in your construction, join OA and OC. That is what we did. So what happens after we've joined OA and OC? You can clearly see that we have created two triangles. That is triangle OJA and triangle OJC. Now, bearing in mind that we need to prove that AJ equals JC. These are the sides of those two triangles, but they are both indifferent triangles. So the best way for you to prove sides are equal, but they are indifferent triangles, is for you to use what we call congruency. So we go on to prove congruency, but in proof of congruency, you must first tell us in which triangles are you going to prove that congruency. So that is in triangle OJA and the other triangle, which is OJC. So what is happening in those triangles? We are first told that from the theorem that OJ is perpendicular to AC. So remember that when lines are perpendicular, they form the angle of 90 degrees, that is right angles. So we can clearly see that your angle OJA in triangle OJA is equals to the other angle, which is 90 degrees, that is OJC. Why are they equal? Because we were told that OJ is perpendicular to AC, and that is why we've got those angles that are equal because they are both equals to 90 degrees. Then we constructed OA and OC, and we can see that OA and OC, these are the radii of the circle, and they are also the hypotenuse of the triangles, and the radii of the circle are equal. So we can go on and say the radii, which is OA, equals to OC, and that is the reason. Those are the radii of the circle. Then we can see that the yellow side on both triangles, which is OJ, it's similar, it's common. Then we can say that OJ is common. Why common? Because it is found in both those triangles. And that is all you have to say. When you say OJ is common, you are basically giving the reason and the statement at the same time. So now that we have proven 3 things about those two triangles, we can conclude that therefore triangle OJA is congruent to triangle OJC. But why are they congruent? It is because we have said that the angle OJA and OJC are equal, and those are the right angles. So those are the right angles. And we said that OA is equals to OC, and those are the radii. I said those are the radii, but also the hypotenuse of the triangles. So that is the hypotenuse. And the last thing is that they are sides which are equal because they are common. So basically, this is your reason: right angle, hypotenuse, and the side. So that is RHS. So this is the reason for your congruency. Now remember that the word congruency means that things are the same with all the aspects. So it means the triangle OJA and triangle OJC, everything about them is the same, and including the side AJ in triangle OJA, which is going to be equals to the side JC in triangle OJC. So that is the conclusion that we can make now. We can conclude that therefore AJ is indeed equals to JC. And that's how you prove the first theorem. Now moving on to the next theorem, it says the line drawn from the center of a circle that bisects a chord is perpendicular to the chord. So in this case, we are again given the circle with the center O and the line that is drawn from the circle. But in this instance, the line is bisecting the chord, making sure that AJ equals AC. So let's see what is required to be proven. So we are required here, it says prove that OJ is perpendicular to AC. We know that OJ bisect AC, but we still need to prove that uh, angle J2 and angle J1 are 90 degrees, and that is what's going to make OJ to be perpendicular to AC. So let's go on and do that. We can see again here, and the first thing that was done in our proof here is construction. So we're going to go on and write that we have constructed. So we're going to say construction. What did we do? What do you do in your construction? You join OA and OC. So after doing that, as we saw in the previous one, we have created two triangles. So to prove that two angles are equal and they are indifferent triangles, another thing that we can use here, the other thing which is the same thing that we used in the previous one, it is congruency. And I said that in congruency, you need to say in which triangles you are working within. So that is in triangle, it's OJA again, and triangle OJC. What is happening there? We were given that AJ equals to AC by those red markings there. So we can start with that. You can start with any sides or anything that you see there. So AJ equals JC. We're saying that because that is given to us. That was given. And again, the OA and the OC are equal because those are the radii. So we can say that your OA equals OC. That is the radii through construction. And again, OJ, which is the yellow side, is common on both triangles. I want to write it this time, this way, this time that OJ equals OJ. And I want to give a reason because it is common. It is the same as saying that OJ is common. Now, because we've proven three things about these two triangles, we can conclude that, therefore, these two triangles are congruent. So we're going to say triangle OJA is congruent to triangle OJC. But what is the reason for this congruency? The reason is because we said sides are equal there, that is A, J, and JC, and the OA and OC, those are also sides, and OJ is also a common side. So that is our reason for congruency: side, side, and a side. And that's that. Nonetheless, we still need to prove that OJ is perpendicular to AC. So you're going to continue here by saying that because we know that these two triangles are congruent, it means everything about them is the same, including the angles, which are corresponding. And those angles, as you can see there, that is angle J1, it is equal to angle J2. We're saying that because of congruent triangle. You can even say congruency, or you can say congruent triangle. But one thing that we see that is that J1 and J2, those are the adjacent side on straight line AC. And we know that adjacent angles on the straight line, they add up to 180 degrees. So we can say that, but we are observing now that your J1 plus your angle J2, this equals 180 degrees. And what is the reason? These are angles on a straight line. So remember that angles on a straight line, they are supplementary, adding up to 180 degrees. But we said that they are equal and they add up to 180 degrees. It means each one of them must have the same number because they are equal. And which same number is that that add up to 180 degrees? That's 90 and 90. If J1 is 90 and J2 is 90, when you add 90 and 90, you get 180 degrees. So it means J1 equals J. We said that J1 equals J2, and they equal because both of them, they equals to 90 degrees. Therefore, we can conclude now that indeed, because of the perpendicular lines meet at 90 degrees, and that is at point J there. So we can conclude that, therefore, your OJ is indeed perpendicular to AC. And that's how you prove that those two lines are indeed perpendicular. Now, the next theorem here, the third one, it says the angle subtended by an arc at the center of the circle is double the size of the angle subtended by the same arc at the circle. Let's talk this through. So it means in this case, we are comparing two angles, one at the center and one at the circumference. And the angle at the circumference, we say that it is the inscribed angle. So the one at the center, it is twice the one at the circumference. Now, as you can see that this theorem comes with different versions. So let's talk these diagrams through. Let's analyze this diagram. We have got angle P on the first diagram, the circumference, and angle O at the center there. And the chord that is subtending these two angles is called QR, as you can see there. So it's called QR there. Now, for you to be able to identify the angle at the center, which is equals to twice the angle at the circumference, which angle is there at the circumference that is going to be twice, or that is going to be half the angle at the center? What you need to do is this. This is what I've just observed when I'm busy with these types of theorems. That you're going to have the angle at the circumference, which is this, and the angle at the center. So I'm just doing the arcs for the angles, and they are subtended by an arc. Can you see the shapes of the arcs here? It's opening upwards for all of them. But what you notice is that the angle at the circumference is looking at the arc, and even this angle at the center is looking at the arc. That's what I see. So this instance, it can even be this way. You can have an angle at the circumference. Here you have got the angle in the center, and you have got your arc there. But look at this. The angle at the circumference is facing the arc, and the angle at the center is also facing the arc. And that's how you're going to identify them. The first instance shows the first diagram. The second one that I've just drawn, it is this. Let us look at this one at the third figure here. You've got the angle at the circumference, which is P, the angle at the center, and they are both subtended by an arc QR, as you can see there. But look at this. This one is facing the arc, and that one is facing the arc. So they are opposite to the arc. That's how you can identify that, which is the same instance here. We have got angle P here. I'm just drawing the arcs. That is the arc for angle P, the arc for angle O in the center, and arc that is subtending those two. So you can see that this one is facing or looking at that one, and also that one is looking at that one. So that is for the first and um, the last figure here. But the one in the middle, it shows us something else. It shows us something else. Now, I want you to look at this. I've been drawing this like this. It's always this angle and this circumference, this angle, and that. So you can see that these arcs, they are always facing the same direction. So you cannot have a situation like when you have this and you have this and you have that. Let's look at this one. The angle at the center, but let's start with the angle at circumference, which is P. The arc for this angle is this one. So you can see the shape of the arc is like that. So it means the shape of the arc for the angle at the circumference should always be like that. Now it means then that this reflex angle, it is the one that is going to be twice the angle at the circumference, because the subtended by this big arc now, this big arc, as you can see now. But you can see that these arcs of ours have got the same um, shape. So it means that this angle cannot be the angle in the center, which is twice the angle of the circumference, because now this arc is facing downwards. So this is basically what you can do to be able to identify the angle of the center and the angle of the circumference in this relationship of one being twice the other or one being half of the other. So that's how you can do it. Nonetheless, we still need to prove this theorem. So going to the next slide. The first thing that I want us to do before we can prove this theorem, it is to remind ourselves of what we used to do in previous grades. So what we have here is the figure on the right hand side, not the circle, but the figure on the right hand side. It is a triangle ABC, as you can see there. In triangle ABC, I've got side AC extended to D in a straight line. It is a straight line. So AD is a straight line. But AC is the side of a triangle. C is the extended side. Now, when you do that, you extend one side of a figure, you form the exterior angle. So in this case, the exterior angle that is formed is this one. I'm going to call it C1, and we're going to have C2 inside there. Now, this is a property of a triangle, that if you've got the exterior angle of a triangle, it is equals to the opposite interior angles that are inside your triangle. So we can conclude here by saying that your angle C1, which is the exterior angle C1 equals angle A plus angle B. Why are they equal? Because C1 is the exterior angle and is equal to the sum of the two opposite interior angles. So the reason is the exterior angle of a triangle. I just wanted to remind you of that. Nonetheless, triangle ABC, it is also an isosceles triangle. How do we see that? This markings here on AC and that one on AB, it tells us that ABC is an isosceles triangle. Now, it being an isosceles triangle, what we know about an isosceles triangle is that the base angles, or the angles opposite the sides that are equal, they are also equal. So what we notice here is that angle B here is opposite side AC, as you can see there, and angle A here is opposite side BC. So these angles that are opposite equal sides are also equal. So that's what we can see, because that is another property of the triangle. We can say that angle A equals angle B. Why are they equal? Because these are angles opposite equal sides. Exactly. I just wanted to remind you of this. Why? Because it's going to be applied here. It's going to be applied here. But nonetheless, I wanted to take this and apply it here before we can even prove the theorem. Remember, we're still doing geometry. So let's put this into practice. We're going back to this figure of ours. So in here, we're given a circle, PQR, with the triangles inside here. Remember, it is going to be given to you with no dotted lines. So these dotted lines are not going to be there. This is what you're going to construct. So after construction, what do we have? After construction, on the angle that is outside, we've got O1 and O2. And the angles that are inside, we've got P1 and P2. And we can notice now that we've got the radii OP, we've got the radii OQ, and we've got the radii OI. And don't forget that the radius, sorry, radius OP, radius, and those are the radii. And don't forget that the radii of the circle are equal in length. Now, because of them being equal, can you notice that they forming isosceles triangle? Triangle QPO, it is an isosceles triangle, and triangle ROP, it is also an isosceles triangle. So because of that deduction, we can also conclude that your angle P1 in triangle QPO equals angle Q, based on the reason that we have stated that angles opposite equal sides. And again, um, on the other triangle, angle P2 is going to be equals angle R, as you can see there. And again, we can see that this dotted line that is drawn here, it is the extended side of those two triangles. So it forms the exterior angle, angle O1 and angle O2. So O1 here is going to be, as the theorem that we saw, the exterior angle of a triangle, O1 here, it's going to be equals to P1 plus angle Q. We are not yet proving the theorem. We're just taking out what is given there. And also, we can see on the other triangle that O2, angle O2 is going to be equals to P2 plus angle R. This is what we are deducting from what we know about the theorems or the properties of the triangles. But nonetheless, let us go and um, prove this. In all these theorems that you are proving, there's a construction that has to be made. So here we constructed, what do we do? We, okay, let's write here. Through the construction, we draw line OP here and then extend it. So you can say we join OP, which is the radii, draw radii and extend. So after doing that, this is the formation of those two, the two triangles and the formation of the radii inside there. Then what we see here in triangle QPO, in triangle QPO, we can see that our O1, we've already said this. Let us just put it into practice. O1 equals P1 plus angle Q. What is the reason for this? The exterior angle of a triangle. Because Q1 is the exterior angle, O1 is the exterior angle of a triangle there. But nonetheless, we can see that because we've got an isosceles triangle, our angle P1 there equals angle Q. Why are they equal? Because those are angles opposite equal sides. You can see that I'm repeating what I've just done there. So it becomes easy for you to see what I'm doing now. So because we're saying that P1 is equals to Q, instead of this Q on the previous statement here, we can just write it as P1. So you're going to have P1 plus P1. So we can conclude that your angle O1 is equals to P1 plus P1. And what is P1 plus P1? That is 2P1. That is P by just substituting P1 is in place of Q. So we did this in triangle QPO. Because these two triangles are the same, we can say that similarly, we can prove that O2 in that other triangle, it is going to be equal to what? 2P2. But remember what we are required to prove. We are required to prove that QOR, which is QOR is equals to 2QPR. But let's talk about QOR, angle QOR. It is made up of O1 plus O2. Can you see that? It is made up of O1 plus O2. So let's go on and do our algebra and add O1 and O2. So O1 plus O2, I'm adding those angles. And remember that O1 is 2P1. So it's the same as 2P1 plus O2, which is 2P2. So I've just added that. Now I'm seeing 2 twice on the right hand side of the equal sign. I don't want to see it twice. I want to see it only once. So I'm going to take it out as a common factor. I'm going to be left with what? P1 plus P2. I hope you can see that. I just wrote 2P2 there. It's just P2. That is just P2 because I've taken P2 as the common factor. I've just taken it out as the common factor there. Now I'm just erasing here because I want space for me to continue writing on the other side. So let me rewrite this. We said that O1 plus O2 is equals to 2 into P1 plus P2. I want to continue from here. But O1 plus O2, it is basically this angle QOR. So that is angle QOR equals to twice Q1 plus P2. And angle QPR, it is made up of Q1 plus Q2. So instead of P1 plus P2, I can just write that as Q angle PR. So I'm just going to go on and do that. That is Q angle PR. And this is what we were required to prove because the theorem it's stating that the angle at the center is twice the angle at the circumference, and that is exactly what is required for us to prove. So that's how you can prove that. Remember that some of this information, it was just an extra information for you to be able to understand what is exactly happening here. Now, that is the information that you can use if you want to reach us. And you can see that we've got affordable rates for our online tutoring. So you can just pause the video and take the information. We'll be happy to hear from you. Now, going to the next theorem, it says opposite angles of a cyclic quadrilateral are supplementary. The word supplementary means that they add up to 180 degrees. So they add up to 180 degrees. That is the word supplementary. Now, here we are given a four-sided figure inside a circle with the vertices on the circumference of the circle. So indeed, that is a cyclic quad, because why would all the 4 points be on the circle if it's not a cyclic quad? But we still need to prove that this is a cyclic quad. So if we can prove that angle D here plus angle E there, which is the opposite side. D and E are opposite to each other, not the opposite side, but the opposite angle. D and E are opposite angles to each other. If you can prove that the sum of D and E equals 180 degrees, and that is going to be the cyclic quad. Why? Because the theorem says the opposite angle of a cyclic quad are supplementary. So we still need to prove that. And as the rule, For us to be able to prove something like this, we first need to construct. So this is what I did. I've constructed here, I joined OC with OF. Now, you can see that we are always constructing if we want to prove something. So this is what we have now. Now, after we have constructed, let me just write what we did before I can move on from construction. Let me just write because I did it, but you need to do it first. That is construction. Our construction, what did we do? We joined O, C, and OF. That is the construction that we did there. Now, remember what I said about the identification of the angles at center. Let us go on and do that. Let us go on and do that. Let's look at this. This angle O1 here, the arc is facing upwards. It is at the center. And this angle here, the arc is also facing upwards, and they are subtended by this arc CF. I don't want to ruin this diagram of ours, but it's subtended by that. Can you see the relationship now? Angle D subtended by CF at the circumference, angle O1 subtended by CF at the center. So it means then that O1 is twice angle D. That is what we see there. And again, the other thing that we see here is this. Now, your O1, which is the reflex angle, your O1, which is the reflex angle, here, look at the shape of the arc and this shape of the arc, and then they are subtended by this big arc. You can see that. So it means that O2 is twice the angle at the circumference, which is 2. So that's how you identify the angles at the center in relation to the angle at the circumference, and using the theorem that says angle at the center is twice the angle at the circumference. So let us go on and use this. So we said that angle O1 equals twice angle D. What is the reason? Angle at center equals 2 times angle at circumference. So that is the reason. And we have identified also that angle O2 equals twice angle E for the same reason, which I'm not going to write, but it is the same reason. That is what we have there. But what is happening at the center then? We've got two angles, O1 and O2, and they are around that center. They form a revolution. And the angles that are around that center, which is the point, they're equals to 360 degrees. So let's do the algebra and add those two angles. So which two angles are at the center? It's angle O1 and angle O2. We are just adding them. And we know that when we add the angles around the point, what do we get? We get 360 degrees. But we still have to give a reason. Why does it give 360 degrees? It is because those are angles around a point. Those are angles around the point. But what is O1? O1, remember, it is 2D and O2 is 2E. So instead of O1 and O2, we can just write 2D. This is your O1. Your O2 is 2E. And that it still equals to 360 degrees. Now, what we can do here, As I said, I'm seeing 2 twice, 2 here at D, 2 there at E. It is the highest common factor. So I'm going to take it out as the common factor. Divide by that. Here we're going to have D plus E equals 360 degrees. Then I divide both sides by 2. I'm going to be left with angle D plus angle E. The brackets falls off because I've divided by 2 and they have cancelled. Then 2 divided by 360 is 180 degrees. And indeed, we have proven that angle D plus angle E equals 180 degrees. So it means then that our D, C, E, F, it is indeed a cyclic quadrilateral. And that's how you prove the cyclic quad. That's how you prove this theorem. There are 3 ways of proving if the figure is indeed a cyclic quad. There are 3 ways. I want to start. Let me erase this so that I start this, so that you understand why do we say that. Why? On the previous one, we were just proving the theorem. So, but in questions, you are going to be asked to prove if a figure it is indeed a cyclic quadrilateral. So there are 3 ways for you to do that. On the first diagram, if you are given the figure like that, and you are told that A plus C is equals to 180 degrees, that is angle A plus angle C, the ones that are highlighted there, equals 180 degrees. You can see that A and C are the opposite angles of this cyclic quad. Therefore, you can prove that this is indeed a cyclic quad. If you can prove that the opposite angles are supplementary, you can prove that that is a cyclic quad. So, but you'll be giving here the reason because of we are given that those 2 angles are equal. We are not basically told that this is a cyclic quad. We are told that in this figure, angle A plus angle C add up to 180 degrees. Then your reason here is going to be the converse of the angles that are supplementary of the cyclic quad. I hope you understand that. So because in this case, you didn't use the theorem itself, but you are told something that leads you to agreeing with what the statement is saying, it means you're going to give the reason as the converse. And that's when you give the reason as the converse. Or on the second diagram here, if you can prove that angles, okay, if you are given the angles in the um, same segments and they are equal, in this case, what do we have here? Angle A equals to angle D, because of them having the same arc, the red one. So angle A equals angle D, and angle C equals angle B here. So if you've got either of these, either that or that, then that is going to be a cyclic quad. So the reason here is the converse of the angles in the same segment. We're still going to have videos where we're going to answer questions based on this. And I hope we're going to meet one of the questions that are asking us to prove whether the figure is a cyclic quad by using this. And the other way is when we have got an exterior angle of the diagram, if you can prove that A1, or if it's given, so I keep on saying if you can prove, but in this case it's given. If it's given that angle A1 is equals to angle C, then this figure is a cyclic quad. And again, here you're going to use the converse of the exterior angle of the cyclic quad. But this is not part of the lesson. It is just added here so that you understand that we have got the main proof of the cyclic quad and ways to prove if the figure is indeed the cyclic quad. And learners tend to really get confused there. But nonetheless, let us move to the next theorem. The next theorem says the angle between the tangent to a circle and the chord drawn from the point of contact is equal to the angle in the alternate segment. Now, there's a lot of English here, but let's focus on this. The chord is drawn from the point of contact. Let us identify that. The chord drawn from the point of contact of what? The contact of the tangent and the chord. So here you can see that the blue dot here, this point here, it represents the point where the tangent meets the circle or touches the circle and where the chords are drawn from. So it tells you which chords have to be of significance to you. Which ones are you going to focus on when you deal with the tangent and the chord theorem? So you look at the tangent and you look where is the tangent touching the circle, and you look where are the chords that are drawn in the circle. So you can see that the green chord, which is NK, it's at the point of contact, and KL also, it starts from the point of contact. Now you'll be asking yourself, why do you have the yellow code? The yellow code is there because it is going to help us, the yellow line basically, it is there because it's going to help us to prove this theorem. And you can see that we are told that there's a center. Why do we have the center here? Because in our construction, we need that center in our construction. So let us see exactly how do we prove this and what is it that we need to prove. So it says prove that L angle KM equals N. So let us highlight these angles that are required for us to prove. It is this angle here that is formed between the tangent and the chord, the red chord, and the angle N. Don't be surprised that we're calling this N1. Remember from our previous diagram, it was just N. And the proof is based on this diagram before we construct. So that is equals to N. So it's basically this angle here equals to that angle there. So someone can argue saying that, but that is not N, it's N1. No, our proof is based on the original figure there. So let us go on and prove this. And how do we prove this? There are other two theorems that are involved in this proof, but I believe that you know them. This video is both for grade 11 and grade 12, but those us that are still in grade 11, you may not have done those two theorems, but if you are watching this and you're in grade 12, you have done those theorems. Nonetheless, the two theorems are this. The first one is that the radius and the tangent are perpendicular to each other. This is what you should know. It is a theorem, but I'm just stating the reason. The radius and the tangent are perpendicular to each other. And the other theorem is that the angle in a semisegment is 90 degrees. What is a semisegment? Remember, when we've got a diameter in the circle, it cuts your circle into two segments, and those segments are called semisegments. So the angle that is subtended by a diameter, it is 90 degrees. So the first thing that we do here, for us to be able to prove what needs to be proven here, it is for us to construct. Always the case. We need to construct always. Um, what are we constructing in this case? We are constructing a diameter. Why do we construct the diameter? Because we need this diameter for us to be able to prove this theorem. We need this diameter. So you're going to draw a diameter and somehow join it. So let's write what we are constructing here. You always have to write it down. I'm just going to say const for construct. We construct. I'm going to call this diameter. Okay, construct. I'm going to say draw. Sorry, that is D. That is draw a diameter. K O T. And after you've done that, you're following the dotted lines. And what did we do that? After that, we joined and join TN. That is what we did in our construction. That is what you do also when you prove this diameter. So you follow this as it is. As I said, you must memorize these steps so that you are good to go when you're proving these theorems. Now, after you've done that, remember radius is half of a diameter. So can we agree now that OK is the radius? You do agree with me? You must agree with me. OK is the radius, but KOT is a diameter. And remember that we are talking the theorem here. The reason why I'm stating that OK is the radius, there's a theorem that says that I've just stated it before here. I said that the radius is perpendicular to the tangent. So let us identify the angles that are formed. The angle that is formed when the radius becomes perpendicular to the tangent. That is the angle, the total angle here, K, which is OKM, which is the right angle. I'm just going to highlight that also with yellow so that you can see. I think this yellow is a bit visible. So that is the right angle because of the radius being perpendicular to the tangent. And we said that other theorem that we are using here is, it says that the angle subtended by a diameter is 90 degrees, and that is the angle in the same segment. So to highlight that angle in red, it is this angle. This angle, you can see that it is resting on your diameter. So what is forming those two angles that are 90 degrees? What is basically forming those two angles? Let's write this down. Your N1 and N2, they form that angle of 90 degrees. So you're going to say that your angle N1 plus angle N2 equals 90 degrees, because that is the angle in the same segment. This is the angle that is subtended by a diameter. Then another angle that we have there, that is 90 degrees, is made up of K1 and K2, and that is also 90 degrees. And the reason this time, it is because your radius is perpendicular to the tangent. So they form an angle of 90 degrees. So this is what we have now. I hope you are following what I'm basically doing here. But now, though both these angles are equals to 90 degrees, both these angles are equals to 90 degrees. So they are both equal. Remember, two things that are equal, two things, they are also equal. So we can go on and say that our K1 plus K2 equals angle N1 plus angle N2. Why do we say that? Because they are both equal 90 degrees. So they are both equal. I hope you do understand that. And if you do understand that, um, we notice something after that, that NTKL, it is a cyclic quad. So it being a cyclic quad, remember what I said about a cyclic quad. If you can prove that angles in the same segments are equal, therefore, that is going to make up a cyclic quad. So in this case, the angles that I'm highlighting in blue, which is N2 and K2 here, they are angles in the same segment. You can check that they are both subtended by chord TL, subtended by the same chord. So because they are subtended by the same chord at the circumference, they are called the angle in the same segment. So they are equal. So we can go on and say that your angle N2 equals K2 equals angle K2. But don't forget that we've got the left hand side and the right hand side that are equal to each other. So if angle N2 here equals angle N2, and the sum of each N1 plus N2 and K1 plus K2 equals to 90 degrees, then it means then that I'm going to give you this as an example. I know this is not part of proving this theorem, but I want you to understand this. If N2 is 60, for example, then it means N1 should be 30 degrees. Why? Because you said N1 plus N2 is 90 degrees. I'm reiterating this. This is not part of proving. I'm just showing you something that you should not forget. n1 plus n2 is 90 degrees. So if n2 is 30, and I just chose 60, I'm not saying that n2 is 60, I chose 60, and it makes n1 to be 30 because 30 plus 60 is 90 degrees. So because we're saying that n2 is equals to k2, it means k2 also should be 60 degrees. So if K2 is 60 degrees, and we said that K2 plus K1 is 90 degrees, it means K1 should be 30 degrees. Now, can you see that now? Can you see that now? If N1 is equals to, if N2 is equals to K2, then it also means that your K1 is going to be equals to N1. So that is the conclusion that we are going to make here, that K1 is equals to N1. So therefore, I'm going to use a different color. Therefore, your K1, angle K1 is equals to angle N1. So let's look at these angles and give them this conventional naming. K1, where is K1? K1 is here. I'm going to erase everything so that we can see clearly where is K1. This was just for us to be able to understand. So let us look at our angle K1. K1 is there. Let's give it a conventional naming. That's LKM. So that is your angle L K, because the angle is formed at K, M is equals to N1. What is forming N1? It is just N. Remember, our N here is just for construction, but this N is basically that one. It's basically this N here. You can see that it's formed between the green and the yellow. And let's go back there. It's still formed between the green and the yellow lines. So that is just N, angle N. And this is exactly what we are required to prove, because the proof says prove that LKM is equals to N. And that's how you basically do it. I hope you enjoyed this lesson. And again, that is the information that you guys can use for you to be able to contact us. Those are our numbers there. And we've got also the email. And these are the subjects that we are offering. And you can see that the rates are so affordable. So you can contact us and find yourself having a tutor that is going to tutor you and become an A student. Thank you so much for watching this video, student, and see you in the next one.